Hello everyone and welcome to today's lesson on Gaussian elimination.
Hello everyone. Now I'm going to give an introduction about the Gaussian elimination. Gaussian elimination is a fundamental method in linear algebra which is widely used to solve system of linear equations. Instead of solving equations one by one, this method organizes the coefficients of the variables into a structured form called augmented matrix. Gaussian elimination is used to transform the augmented matrix into a simpler form using elementary row operations. These operations include swapping rows, multiplying a row by a non-zero constant, and adding or subtracting multiple of one row from another. Through a sequence of such steps, the matrix is gradually converted into a row echelon form, where the values of the variables can be easily identified. One of the advantages of using Gaussian elimination is its logical and step-by-step nature. Each transformation is based on preserving the original meaning of the system, ensuring that solution remains unchanged throughout the process. This makes the method both reliable and efficient. Gaussian elimination is not only important in mathematics but also plays a significant role in fields such as computer science, data analysis, and many more. Many computational algorithms used today are built upon this method.
First of all, we will solve a system of equations using Gaussian elimination for a 2 by 2 matrix. The first step is to convert the equations into an augmented matrix. First, we write the system of linear equations in matrix form. We place the coefficients of the variables into the matrix and the constants on the right side after the vertical line. This is called an augmented matrix. Step 2 is to make the first number become 1. Next, we look at the first number in the top left corner of the matrix. The current value is 2. To make it equal to 1, we divide row 1 by 2. We divide every element in row 1, column 2, and column 3 by 2. After dividing, we rewrite the matrix with the updated values. Step 3. Eliminate the number below the first leading one. Now, we want the number below the first one in column 1 to become 0. To do this, we apply a row operation using row 1 to eliminate the value in row 2, column 1. We perform the calculation for each column in row 2 and update the matrix. After this step, the first column will have a 1 at the top and 0 below it. Next, for the step 4, make the second pivot become 1. Next, we focus on the second pivot in row 2. The current value is 2.5. To change it into 1, we divide row 2 by 2.5. Again, we divide every element in row 2, column 1, column 2, and column 3 by 2.5. We then write the new matrix. The last step is to eliminate the number above the second one. Now, we want the number above the second pivot to become 0. Using row 2, we perform a row operation on row 1. We calculate each column carefully and update the matrix. After this step, the matrix is in reduced row echelon form. The values in the last column now represent the solution to the system of equations. These values give us the final answers for the variables.
In this video, I will solve a system of 3 linear equations using the Gaussian elimination method. The given system of equation consists of 3 variables, namely x, y, and z. First, we write the given equations. X plus y plus z equals to 6, 2x plus y minus z equals to 3, and negative x plus 2y plus 3z equals to 14. Next, we take the coefficients of x, y, and z together with the constant terms and arrange them into an augmented matrix. The augmented matrix is 1, 1, 1, 6, 2, 1, negative 1, 3, and negative 1, 2, 3, and 14. Now we look at the element in row 1, column 1. Since the value is already 1, it is already a suitable pivot. Therefore, no row operation is required at this step. Next, we eliminate the x values before the first pivot. For row 2, we subtract 2 times row 1 from row 2. This operation changes row 2 into 0, -1, -3, and -9. For row 3, we add row 1 to row 3. The results in 0, 3, 4, and 20. After this operation, the first column below the pivot becomes 0. Step 4. Now we focus on the second row and second column. The pivot value is -1. To convert it into 1, we multiply the entire second row by -1. This gives us a new second row with values 0, 1, 3, and 9. Step 5. We eliminate below and above the second pivot. Next, we eliminate the y value below the second pivot. To do this, we subtract 3 times row 2 for row 3. This changes row 3 into 0, 0, -5, and -7. Then, we eliminate the y value above the second pivot by subtracting row 2 from row 1. This gives a new first row of 1, 0, -2, and -3. Step 6. Now, we move to third row. The pivot value in the z column is -5. To make it equal to 1, we divide the entire third row by -5. As a result, the third row becomes 0, 0, 1, and 7/5. Step 7. We eliminate the z values above the third pivot. For row 2, we subtract 3 times row 3 from row 2. This results in 0, 1, 0, and 24/5. For row 1, we add 2 times row 3 to row 1. This gives 1, 0, 0, and -1/5. At this point, the matrix is in reduced row echelon form. From the final matrix, we directly read the values of the variables. X is equals to -1/5, Y is equals to 24/5, and Z is equals to 7/5.
Today we'll be solving a 3-variable system using Gaussian elimination. The goal is to convert the system into a matrix form and use row operations to reach a simplified form where we can read of x, y, and z. Step 1 is translating the system into an augmented matrix. Take the coefficients of x, y, and z and then place them in columns, and the constants go in the last column after the vertical bar. And then our first pivot is the top left entry. It's currently 2, so I divide the entire first row by 2 to make that pivot equal to 1. This makes elimination cleaner in the next step. Now we want zeros underneath the pivot in column 1. For row 2, I add 3 times row 1 to row 2. That cancels the -3 and creates a 0 in column 1. And then apply the same operation across the entire row, including the constant. Next, eliminate the entry under the pivot in row 3, column 1. Since row 3 starts with -2, so I add 2 times row 1 to row 3. Again, do it to every entry in that row, so the equations stay equivalent. The second pivot is in row 2, column 1. It's 0.5, so multiply row 2 by 2 to make it 1. Now row 2 becomes the pivot row for clearing out column 2 above and below. Now clear the column 2. First, eliminate the 2 in row 3 by subtracting 2 times row 2. Then, eliminate the 0.5 in row 1 by subtracting 0.5 times row 2. After that, column 2 has a clean pivot with zeros above and below. Now, onto the third pivot, which is in row 3, column 3, and it's currently -1. So multiply the entire row 3 by -1, so the pivot becomes +1. Now we clear out the entries above the third pivot. Since row 2 has a 1 in column 3, so we have to subtract row 3 from row 2. Since row 1 has negative 1 in column 3, so add row 3 to row 1. Now the matrix is in reduced row echelon form, so we can read the solution directly. So now we get our answer, which is x equal to 2, y equal to 3, and z equal to negative 1. To confirm if this answer is are correct, so we have to substitute back into each original equations. If we get the same number, so that means it's correct.
That brings us to the end of this lesson on Gaussian elimination. We have learned how to solve both 2 times 2 and 3 times 3 system of equation using augmented matrix and elementary row operation. To conclude, Gaussian elimination is a systematic and reliable method for solving system of linear equation. By converting equation into an augmented matrix, we are able to organize all the information in a clear and structured way. The use of elementary row operation allow us to simplify the matrix step by step while still preserving the original solution of the system. Once the matrix is in its final form, the value of the variable can be identified easily without additional calculations. Thank you for watching, and we hope this lesson was helpful.